In our last class, we started looking at the concept of frequency response, which is an extension of sinusoidal steady-state analysis. In sinusoidal steady-state analysis, we consider the case where a circuit is being driven by a sinusoidal input, and we find the output voltages and currents using the concepts of phasors and impedances. In frequency response, we took this a step further. Rather than looking at the input at just a single frequency, we're looking at the circuit's overall response to the input for a wide range of frequencies. And we introduced something called the transfer function, which was a complex function which related the input phasor to the output phasor. And we also looked at something called the frequency response plot, which were graphical views of how the circuit adjusts the input as a function of frequency. So last class, we did this example where we had an input signal Vn of t driving a resistor-capacitor combination, and we wanted to find the voltage across the capacitor. So we found the transfer function to be h of omega was 1 over 1 plus j omega over 1,000. And we saw that that in turn could be broken down into its magnitude response, which was just 1 over the square root of 1 plus omega squared over 10 to the 6th, and its phase response, which was nothing more than negative inverse tangent of omega over 1,000. We also did an example where we used the transfer function to calculate the output voltage for 3 specific input signals, one at 200 radians per second, one at 3,000 radians per second, and one at 10 to the 5th radians per second. In each case, we plugged the frequency into the transfer function, and when you evaluated it, you got a complex number, and the magnitude of that complex number gets multiplied by the magnitude of the input signal to give you the magnitude of the output signal, and the phase of that complex number gets added to the phase of the input signal to give you the phase of the output signal. So for example, we saw that 2 cosine of 200t plus 45 degrees yielded an output voltage of 1.96 cosine of 200t plus 33.7 degrees. And we saw that an input of 2 cosine of 3000t minus 20 degrees gave us an output of 0.63246 cosine 3000t minus 91.6 degrees. And finally, we saw that an input of 2 cosine 10 to the 5th t plus 15 degrees gave us an output of 0.019999 cosine of 10 to the 5th t minus 74.43 degrees. We also saw that if you plotted the h of omega magnitude response and phase response and did it as a Bode plot, we got these two plots here. What we're going to do now is use these Bode plots to estimate the output for given input signals. So rather than evaluating this function at the frequencies of 200, 3000, and 10 to the 5th radians per second, we're going to take those frequencies and plug them into the Bode plot and use an eyeball measurement to determine approximately what the magnitude and phase would be. So let's do that now. So in the case where omega is 200 radians per second, if you go to the Bode plot, 200 radians per second is this line right here. So eyeballing that, you really don't see that amplitude being anything different than 0 dB. So we say it's approximately 0 dB, which of course corresponds to a gain of 1. Phase, once again at 200 radians per second, is approximately minus 10 degrees. That's about as close as we can approximate based upon the resolution that we have in this figure. So going back here, at a frequency of 200 radians per second, V out sub 1 of t is approximately what? It's approximately 2 times 1 times cosine of 200t plus 45 degrees minus 10 degrees, which is 2 cosine 200t plus 35 degrees volts. Once again, this value here and here came from the Bode plot on the next page. If you compare this with the exact value, you see that it's close, but it's not exact. But it's a very quick approximation. Let's do the same thing for the second signal at 3000 radians per second. So here, 3000, let's see, here's 1000, so that's 2000. That is 3000 right there, there, and there. So the magnitude plot is approximately minus 10 dB. And if you remember, the relationship between gain in dB is the gain is equal to 10 to the dB gain divided by 20. So this is now 10 to the minus 10 over 20, or 0.316. If you look at the phase, once again, it's an approximation. It looks like it's about at minus 72 degrees. So in this case, V out 2 is approximately 2 times 0.316 times cosine of 3000t minus 20 degrees minus 72 degrees, which is 0.632 cosine 3000t minus 92 degrees. Once again, it's close, but not exactly identical to what you get if you plug 3000 into the transfer function. And when omega is 10 to the 5th radians per second, 10 to the 5th is down here. The magnitude is approximately minus 40 dB, which once again is a gain of 0.01, and the phase looks to be at minus 90 degrees. So the third estimate, V out sub 3, is approximately equal to 2 times 0.01 cosine 10 to the 5th t plus 15 degrees minus 90 degrees, which is 0.02 cosine 10 to the 5th t minus 75 degrees. And this is close to, but not identical to, what you get plugging things in and doing the math exactly. Bottom line, we could use the Bode plot to get a quick estimate of what the output voltage or current would be without doing all of the math. Let's now spend a little bit of time comparing the transfer function equation and the Bode plots. So the transfer function was h of omega equal to 1 over 1 plus j omega over 1000. Think about what happens when the frequency is small. When the frequency is small, the imaginary part of the denominator is going to be a small number, 0.01, 0.05, 0.1, etc. And so the magnitude of the denominator of h of omega is going to be just slightly larger than 1. And so the ratio of the two magnitudes is going to be approximately 1 or 0 dB. What happens as omega starts increasing, the imaginary part of the denominator gets larger and larger, which means the magnitude of the denominator gets larger and larger. So the ratio of the numerator to the denominator gets smaller and smaller. And for very large omegas, for example, when omega is 5,000 or 10,000 or 100,000, the denominator has a magnitude much larger than the numerator, and what we see is eventually the magnitude of the frequency response drops considerably. At what point do we start seeing that big difference? We start seeing that when omega is equal to 1,000. When omega equals 1,000 is where we start seeing that the imaginary part of the denominator starts having a much bigger effect than the real part. We call this frequency the breakpoint. The breakpoint is basically the boundary between where the denominator does not have a big effect to where it does have the big effect. Everything to the left of the breakpoint we're going to call the passband. In the passband, input frequencies basically show up at the output with a gain close to 0 dB or 1. To the right of the breakpoint, we're going to call that the stop band. The stop band represents frequencies where there's much attenuation between the input and the output. If you evaluate h of omega right at the breakpoint, what do we see? We get 1 over 1 plus j1, which in polar coordinates is 1 at an angle of 0 over the square root of 2 at an angle of 45 degrees. 1 over the square root of 2 is 0.707 or minus 3 dB, and sure enough, at this breakpoint, the magnitude response is minus 3 dB. So we also call this breakpoint the 3 dB point. And once again, it is the boundary between the passband and the stop band. Another point here is, where does this 1,000 come from? This 1,000, if you look back at the problem when we first came up with the transfer function, this 1,000 is just 1 over RC. And so we see that the breakpoint is nothing more than the reciprocal of the time constant of the RC circuit. So they're all very much related. Let's look at the phase briefly. Once again, at very low frequencies, the imaginary part of the denominator is going to be a very small number. And so the angle of a number like 1 plus j 0.04 or 1 plus j 0.07 is going to have just a very small positive angle. So when you subtract the denominator angle from the numerator angle, you get 0 degrees minus a small positive angle, you get a small negative angle. So for low frequencies, you get a small negative angle. As we start increasing the frequency, however, the angle of the denominator becomes larger and larger. So when it's subtracted from 0, we get a larger negative number. In fact, what happens at the break frequency, we get a denominator angle of 45 degrees. And so we see that at the break frequency, the phase is negative 45 degrees. By the time you get to really, really large frequencies, we see a denominator angle that's close to 90 degrees. 1 plus j 1,000, for example, has an angle very close to 90 degrees. When you subtract that from 0, you're going to get negative 90 degrees, and that's exactly what we see happening here. So this example is what is called a low-pass filter. I think what this circuit does is it allows low frequencies, frequencies less than the breakpoint frequencies, to basically pass through the circuit with a gain close to 1. For frequencies greater than the breakpoint, we start seeing attenuation. Not a lot of attenuation at first, but as you get really far away from 1,000 radians per second, the attenuation is great. Once again, you have to remember, these are in dB, so minus 40 is actually 0.01, which is a pretty big amount of attenuation. It's a 100-fold attenuation. So let's extend this idea to something that we call frequency selective filters. So what is a frequency selective filter? It's a circuit that uses the frequency dependency of capacitors and inductors to allow certain frequencies to pass through the system and other frequencies to be blocked from passing through the system. What we saw in the previous example is what's called a low-pass filter. It allows low frequencies to pass through. So it's going to have a frequency response. So it's basically something like this. Low frequencies can pass through. High frequencies are attenuated. A high-pass filter does just the opposite. It allows high frequencies to pass through. So it's going to have a frequency response that starts at 0 and goes up and lets high frequencies pass through. A band-pass filter will allow a range of frequencies to pass through. So a band-pass filter is going to have a magnitude frequency response that looks something like that. A band-stop filter does the exact opposite. It blocks a range of frequencies from passing through. So at low frequencies and high frequencies, it will let the signal pass through, but in between it will block. And there's a subset of band-stop filters called notch filters that block a single frequency. So a notch filter would look something like that. And as we saw, the RC circuit that we started with is an example of a low-pass filter. It lets low frequencies pass, and it blocks high frequencies. And if you think about this from the perspective of the capacitor being a frequency-dependent impedance, this makes a lot of sense. For low frequencies, the capacitor looks like an open circuit. So if you use voltage division, this impedance over the sum of these two impedances is going to be close to 1 or 0 dB. As our frequency goes up, the impedance of the capacitor goes down. So now the ratio of the capacitor impedance to the capacitor plus resistor is going to be a number much less than 1, and we start getting our lower gains. So where are these frequency selective filters used? Well, there are lots of different situations and many different types of engineering where they're used. I'm just going to list a couple here. A low-pass filter is very useful, for example, when you want to average data. So suppose you have a signal that has some high frequency variations that really are not meaningful. The low-pass filter smooths those out, basically averaging those values together so that you can just average the signal. Likewise, suppose you have an audio signal with a lot of high-frequency noise or hiss. The low-pass filter, once again, will remove those components from the output so that you do not hear the high-frequency hiss. High-pass filter could be used, for example, if you have a situation where you have a sensor that's measuring some variation, but there's also some slow variation that you're not interested in that's also being picked up by the sensor. A classic example of this is an electrocardiogram where you're trying to measure the heart's performance, but what happens is your breathing can cause some low frequency variations in the signal. You're not interested in those low frequency variations. So the high pass filter will basically remove those low frequency variations, allowing you to concentrate on the high frequency variations associated with the heart itself. Bandpass filters show up a lot in communications. Every time you tune your radio to a particular station, what you are doing is you're basically creating a bandpass filter that's grabbing frequencies in a certain frequency range from the air. So your antenna can pick up a whole bunch of frequency ranges, but the bandpass filter on your radio then concentrates on frequencies in a certain band, in a certain range, a certain radio station, and that's what you actually listen to. Bandpass filters also show up in a graphic equalizer on a stereo. So the idea behind a graphic equalizer is you might want to boost the energy of just a certain range of frequencies in the music. And so you pass the music through a whole bunch of bandpass filters. Maybe there's one bandpass filter somewhere near 1,000 hertz. So all the music that's around 1,000 hertz goes through that bandpass filter, and then you can adjust its amplitude independently from the other frequency bands. Bandstop filters can be used when you want to remove unwanted frequency components from a signal. This happens a lot, for example, when you have 60 hertz noise that creeps through a signal measurement. You want to ignore the 60 hertz component, so you pass your signal through a band stop filter to remove all frequencies close to 60 hertz to solve that problem. So how do we create these high pass, band pass, and band stop filters? Let's look at a few more examples. So this example is like the previous example, except the location of the capacitor and the resistor are switched. So now the capacitor is in the top branch and the resistor is in the branch on the right. So without doing any math, let's think about what happens here. What happens at low frequencies with the capacitor? It looks like an open circuit. So for low frequencies, this capacitor is going to block the signal Vin from showing up at V output. So low frequencies will not appear at the output. As the frequency of the input goes up, the capacitor looks more and more like a short circuit, just a wire. And eventually the capacitor looks just like a wire, and so V output is going to look like V in. So by putting the capacitor in the top branch, we're now creating what we call a high pass filter. It is going to allow high frequencies to show up at the output, but not low frequencies. So this is going to be a high pass filter. We can look at this mathematically just like we did for the previous circuit by drawing the circuit in the phasor domain. So the capacitor in the phasor domain is minus J over omega C, or minus J 2000 over omega ohms. Resistors, impedance is just 2 ohms. It's not a function of frequency. So we have the V in phasor on the left. What we're measuring now is the voltage across the resistor. That's V out phasor. And from voltage division, it equals that impedance over the sum of the two impedances times this input signal. So V out phasor is what? 2 over 2 minus J 2000 over omega times V in tilde. So the transfer function h of omega, by definition, V out over V in, is just 2 over 2 minus J 2000 over omega. We can now divide both the numerator and denominator by 2 to get 1 over 1 minus J 1000 over omega. Let's look at what the magnitude response and the phase response would be. Magnitude response. The magnitude of the numerator is just 1. The magnitude of the denominator is the square root of the real part squared plus the imaginary part squared. The imaginary part is minus 1000 over omega squared. You work out the math. It's 1 over the square root of 1 plus 10 to the 6th over omega squared. Let's look at the phase, or the angle of h of omega. Once again, the angle of the numerator is just 0 degrees. The angle of the denominator is subtracted from the angle of the numerator. So we subtract the angle of a complex number is the inverse tangent of the imaginary over the real. And the inverse tangent of negative x is negative the inverse tangent of x. So this can be rewritten as plus inverse tangent of 1000 over omega. Once again, let's think of what happens at low frequencies and high frequencies. For low frequencies, so for example, h of omega, when omega is equal to 0, the magnitude is what? it's 1 over the square root of 1 plus 10 to the 6th over 0. When you divide by 0, you get infinity. You get 1 over infinity, which is 0. Likewise, when you evaluate this magnitude function with the frequency approaching infinity, you get what? You get 1 over 1 plus 10 to the 6th over infinity. A number over infinity is just 0, so you get 1 over 1, or 1. Finally, at what frequency do we have this break between where the imaginary part of the denominator has a big effect or not? We see that happens once again at 1,000. So you evaluate this at omega equal 1,000, you get 1 over 1 plus 1, 1 over the square root of 2, or minus 3 dB. Likewise, we look at the angle. The angle of h at a frequency of 0 is what? What is the inverse tangent of infinity? Remember, inverse tangent says what angle gives you that slope. What angle gives you a slope of infinity? 90 degrees. When your frequency goes to infinity, now we have the inverse tangent of 1,000 over infinity, inverse tangent of 0. We get 0 degrees. And if we wanted to evaluate it at the break point, 1,000 radians per second, we get what? We get inverse tangent of 1, or 45 degrees. So if you were to plot the magnitude and phase plots here, you would see now that for high frequencies, we get a gain of approximately 1. For low frequencies, we get gains much less than 1. And once again, where is the break point? It is once again at 1,000 radians per second, or 1 over RC. That is the boundary between the passband and the stop band. But now, because of the location of the capacitor and the resistor, we now see that the passband is to the right of the 1,000 radians per second and the stop band is to the left. So we have, once again, a high pass filter. Looking at the phase, once again, we see that it starts at 90 degrees now and eventually makes its way down to 0 degrees. And at the break point, it's minus 45 degrees. So what we see in the Bode plot agrees mathematically with what we saw in the transfer function. So how do you get band pass and band stop filters? Well, now you need more than just a resistor and a capacitor. You need to add an inductor. So let's look at this circuit first. So we have an input signal, Vin, applied to a inductor, capacitor, resistor combination. We have the inductor and the capacitor along the top branch and a resistor on the right branch. And we're measuring the voltage across the resistor. Without doing any math, let's evaluate this a little bit. Think about what happens at very low frequencies. The inductor looks like a short circuit. The capacitor looks like an open circuit. So that means at very low frequencies, the signal gets blocked by the capacitor. At very, very high frequencies, the capacitor now looks like a short circuit. It doesn't block anything, but the inductor looks like an open circuit. So it's going to block the signal flow from input to output. So at high frequencies, the inductor blocks the input from appearing at the output. But what happens in between? There's going to be some frequency in between where the capacitor's impedance is going to cancel the inductor's impedance. Remember, the inductor's impedance is always positive. The capacitor's impedance is always negative. So there's going to be some frequency where you're going to get Jx and minus jx, and you get a total impedance along that top branch of 0, which is just a wire. So there's going to be some middle frequency where the output equals the input. So this is what we call a band pass filter. It blocks low frequencies, it blocks high frequencies, but there's some middle frequency that it's going to let pass through the filter. So let's look at this mathematically. In the phasor domain, the inductor becomes an impedance of j omega L. The capacitor becomes an impedance of minus j over omega C, so minus j 4 over omega. The resistor has a constant impedance, in this case 1 ohm. So Vin is applied here. Vout is measured here. And from voltage division, Vout is going to be that impedance over that plus that plus that times Vin. So it's 1 over 1 plus j 0.04 omega minus 4 over omega times Vin phasor. So the transfer function, which is just the ratio of Vout to Vin, is 1 over 1 plus j 0.04 omega minus 4 over omega. What we'll do is let's multiply the numerator and denominator both by omega to get a slightly different form. H of omega now is omega over omega plus j 0.04 omega squared minus 4. This is our transfer function in this case. As with the low pass and high pass filters, from this we can calculate the magnitude response and the phase response. The magnitude response, the magnitude of this function, is what? What is the magnitude of the numerator? The magnitude of omega is omega. What is the magnitude of the denominator? Once again, the magnitude of the complex number is the square root of the real part squared plus the imaginary part squared. 0.04 omega squared minus 4 squared. What is the phase or angle of this function? It's the angle of the numerator minus the angle of the denominator. What's the angle of the numerator? The numerator is just a real number, omega. The angle of a real number is always 0 degrees. From that we subtract the angle of the denominator. The angle of the denominator is the inverse tangent of the imaginary over the real. So let's look at these at both really low frequencies and really high frequencies and then middle frequencies. In particular, we're concerned about the magnitude response. So look at the magnitude of H evaluated at omega equal to 0. We're going to get 0 over the square root of 0 plus 0 minus 4 squared, and you're going to get 0. So at low frequencies, the gain is going to be 0. Once again, that's because the capacitor blocks the signal. So now let's look at high frequencies. So the magnitude of H as omega approaches infinity, you get some large number in the numerator. In the denominator, you get what? You get the same large number squared plus 0.04 times that large number squared minus 4 and then another square. Because in the denominator you have this large number squared and squared again, and then you're taking the square root, you see that you're going to have the denominator much larger than the numerator, and so once again, that is going to be 0. Finally, let's look at the frequency where that part equals 0. So if you set 0.04 omega squared equal to 4, or omega squared of 100, or omega equals 10 radians per second, what do we get? We get 10 over the square root of 10 squared plus 0 or 1. So what we see for low frequencies, we get a gain of 0. For high frequencies, we get a gain of 0. And at this particular middle frequency, we get a gain of 1. If you look at the Bode plot, sure enough, we see that happening. We see that for low frequencies, you get a lot of attenuation. Likewise, for high frequencies, you get a lot of attenuation. And there's a small range of frequencies in the middle where you get a gain close to unity or 0 dB. In fact, at this point right here, we do get a gain of 1 or 0 dB. In this case, we call this point the midpoint of the passband. It is the frequency at which we get maximum gain of unity. Turns out that what frequency does it happen at? It happens at a frequency of 1 over the square root of LC. You might remember this from LC oscillator circuits. It is the frequency of oscillation when you have a lossless LC circuit. In this case, where you have an RLC circuit, this frequency also gives us the midpoint of what we call the passband. So this range here is called a stop band. This range here is what we call a stop band. And then in between is what we call the passband. Now, at what point do we say that we're in the passband rather than the stop band? Well, that can vary depending upon the application, but typically you might choose the point where it's at minus 3 dB. And so the midpoint of the passband comes from the value of the inductor and the capacitor. The width of the passband depends upon R. So this width depends on R. Basically, we see that as R goes up, the passband width becomes wider. And here we get our bandpass filter, where once again the value of the capacitor and the inductor dictate where it is centered, and the value of the resistor dictates how wide it's going to be. In this class, we're not going to worry too much about the phase plot for a bandpass filter. But if you were to take this function here and plot it as a function of omega, you would see that it looks something like this plot here. So let's do one last example. Let's look at a situation where we have an RLC circuit, but now the capacitor and inductor are in the rightmost branch and the resistor is in the top branch. Once again, let's think about what happens at low frequencies and high frequencies before we do any math. At low frequencies, the capacitor is an open circuit, the inductor is a short circuit. Because the capacitor is an open circuit, this right branch is open, and basically you just have the signal going from the input to the resistor to the output. Likewise, at high frequencies, now the capacitor is a short circuit, but the inductor is an open circuit. So once again, you have the input signal just traveling through the resistor to the output. However, what happens at some middle frequency? There's going to be some frequency where the capacitor's impedance cancels the inductor's impedance. So maybe the inductor impedance is J10 and the capacitor impedance would be negative J10. Regardless of what the values are, when you add them together, you're going to get 0 or a wire, and V out is going to be shorted and going to be 0. So what we see in this situation is low frequencies pass through to the output without any attenuation. High frequencies pass through to the output without any attenuation. And there's going to be some middle frequency where the output's going to be shorted. So this is a band stop filter. Let's look at this mathematically. In the phasor domain, the resistor is a 1 ohm impedance. The inductor is an impedance of J.04 omega. The capacitor is an impedance of minus J4 over omega. And we're measuring the voltage across the capacitor-inductor combination. From voltage division, what do we get? We get J times 0.04 omega minus 4 over omega over 1 plus that. All that times V in phasor. So H of omega, which is just the output phasor over the input phasor, is what? It's J times 0.04 omega minus 4 over omega over 1 plus that, same term. We can now multiply the numerator and the denominator by omega to get a slightly different variation. We get 0.04 omega squared minus 4 over omega plus J, 0.04 omega squared minus 4. This is our transfer function. We can separately calculate the magnitude response. So the magnitude response, the numerator is now going to be an imaginary number. So the magnitude of it is just the argument of the J term, and we do need to use absolute values here because depending upon the value of omega, 0.04 omega squared minus 4 could be a positive or a negative number. So we use the absolute value because we're interested in the magnitude. And once again, the magnitude of the denominator is a square root of the real part squared plus the imaginary part squared. The angle is really tricky here. Think about the angle of the numerator. The numerator is an imaginary number that could be either positive or negative. If the frequency is less than 10 radians per second, 0.04 omega squared minus 4 is going to be negative, so we get something like negative J6, negative J10, whatever, and it has an angle of minus 90 degrees. So the numerator angle is going to be minus 90 degrees minus the denominator angle, which is the inverse tangent of 0.04 omega squared minus 4 over omega. So that's going to be the equation for a frequency of less than 10 radians per second. When omega is greater than 10 radians per second, the numerator of h of omega is now a positive imaginary number, so it's going to have an angle of 90 degrees. And once again, we subtract the angle of the denominator, 0.04 omega squared minus 4 over omega. And that's our frequency greater than 10 radians per second. So you see it's a little trickier than in the low pass, high pass, or band pass cases. Let's spend a couple minutes looking at specifically the magnitude response for low frequencies, high frequencies, and some middle frequency. So the magnitude of h of omega evaluated at omega equals 0 is what? The numerator just becomes 4. The denominator, you get the square root of 0 plus 0 minus 4 squared. So you get 4 over the square root of 16, or 1. How about the magnitude when the frequency approaches infinity? Now, the numerator is going to be some large number squared. The denominator is going to be the square root of a large number squared plus another large number squared squared. Here, once again, we see that becomes 1. What about when this part in parentheses equals 0? So when 0.04 omega squared equals 4, or omega equals 10 radians per second, we get what? We get h of omega equal 0 over the square root of 10 squared, or 0. So once again, we see that at low frequencies, we get a gain of 1. At high frequencies, we get a gain of 1. And at this 1 middle frequency, we get a gain of 0, or a bandstop filter. And if we now plot this magnitude equation and this phase equation on a Bode plot, we see exactly that. We see that for low frequencies, we get a gain approximately equal to 0 dB. Likewise, for high frequencies, same thing. At some middle frequencies, all of a sudden, this number here gets very, very small, and in fact, at 10 radians per second, it gets 0. So we see that in the vicinity of 10 radians per second, we start getting the frequency response dropping. And in fact, at 10 radians per second, we get a gain of 0 or minus infinity dB. Now in this plot, it looks like it's at minus 50. That's just because we don't have a lot of resolution. But it actually goes to minus infinity dB at that frequency. And what is this frequency? This frequency is 1 over the square root of LC. So just like in the band pass filter, in this filter called a band stop filter, we see that the value of the capacitor and the inductor dictates the midpoint of the stop band. So this is a pass band on the left. This is another pass band on the right. And in the middle, we get a stop band. The midpoint of the stop band is dictated by the capacitor and the inductor value. And just like in the band pass case, the width depends upon R. As the resistance value goes up, we get a wider stop band. Phase plot, once again, we're not going to worry too much about. I do want to point out what's happening right here. At 10 radians per second, if you look at what happens in this equation here, 10 radians per second is a frequency at which this numerator jumps from a negative imaginary number to a positive imaginary number. So the change in sign that happens at 10 radians per second, a change in sign in a phase becomes a 180-degree jump. And that's exactly what happens. We jump from minus 90 degrees to plus 90 degrees. Once again, the details of the phase plot are really beyond the scope of this course. We're much more concerned about The magnitude plot, or in this example here, we see what's called a band stop filter. We're passing low frequencies, we're passing high frequencies, and we're stopping frequencies in the middle. We will continue with this topic next class. Until then, have a good day.